Hello students, in this video we'll discuss ordering properties of the multiplication operator on the natural numbers. Here's our first result. Our first result states the following. If n is less than m, n is equal to m, or m is less than n is greater than m. So I have three separate cases. These cases exhaust all the cases with n and m in natural numbers. For n and n in n, then n times p less than m times p, n times p equals m times p, or n times p bigger than m times p for any p and n respectively. What that means that if n is less than m, then n times p is less than m times p. If n is equal to m, then n times p is equal to m times p. And if n is bigger than m, then it's the case that n times p is bigger than m times p, right? The second case is trivial, so the proof of this, n equals m, implies n times p equals m times p, since multiplication is well defined. That follows from the definition of multiplication. Now let's assume one of the cases, the other case is similar. If n is less than m, then what does this imply? This is equivalent to saying there is a q in n such that what? Well, m is larger than n. That says that m is equal to n plus q. That's the definition of that ordering. Now, if I multiply this relationship and use the distributive property of multiplication, this implies that m times p is equal to n plus q times p, and now we know that multiplication is distributive. We proved that already. So this is equal to np plus qp, and this expression over here tells me that np is less than mp. This is exactly equivalent to saying that np is less than mp, and that gives us a result. The other case, this case over here, is exactly equivalent. I just flipped the order of everything. Let's prove our second theorem. Our second theorem actually just follows immediately from this. The second theorem states that if n times p is less than m times p, or np equals mp, or np bigger than mp, then what? Then n less than m, or n equals m, or n bigger than m, respectively. Okay? And the proof of this follows from the previous theorem. In other words, all of these cases over here, exhaust every possible case for ordering m and n. So this theorem, the proof, follows from previous theorem. Since the cases n less than m, n equals m, and n bigger than m exhaust all possibilities. And this gives us our first sort of cancellation result. In other words, I can cancel out the p in some sense, right? I multiply my natural numbers, assuming, of course, that p is a natural number, so it's a positive number over here. So positive cancellation preserves the sense of the inequality. When we construct the negative numbers from negative Dedekind cuts, we'll see that the sense of the inequality will change. So the final result is this, one more result on ordering. And what's that last result on ordering of the natural numbers? That says that if n is less than m, and what? And let's say that p is less than q, where of course here n, m, p, and q are in n. Then n times p then n times p is less than is less than m times q. And so, of course, the proof of this is as follows. So we prove this in the following way. Well, this first statement over here says that m is equal to n plus a. And this statement over here says that q is equal to p plus b. And so now I can consider m times q. So m times q then, m times q is equal to n plus a times p plus b. And now I can FOIL, I can distribute twice, or FOIL traditionally. So by my distributive law of multiplication, I can write this by, I'm going to simultaneously in this step use all of the properties we've proven. I'm going to distribute, I'm going to associate, and I'm going to commute as basically at will. And by using all of those properties, distributivity, associativity, and commutativity, I can write this as np plus ap plus nb plus ab, and I'm not writing down any parentheses over here because the associativity says that the order doesn't matter. And so now I can use associativity over and over and over again to give this expression over here meaning. Now what that tells me, it tells me that mq is equal to np plus another natural number over here. It's a combination of multiplications and additions. What this tells us over here is that mq is what? Then mq is larger than np, and that gives us our result. So these summarize the fundamental ordering properties of the multiplication operator over the natural numbers. Thank you very much.